This is a final lecture where my goal is to tie various loose ends. So we've described the spin chain model in some detail, and I've started discussing the continuum model. So the loose ends that I would like to tie up today are the correspondence between these two sides of the blackboard. What exactly is the role of charge conjugation? I'll also make some comments about the symmetry enhancement here, and then I'll describe some domain walls here, and I'll give you a continuum proof that this model has a discrete anomaly, and in fact it cannot go trivial gapped in some strongly coupled regime away from the large mass regime where we can do semi-classical analysis. So I'll give you the proof, and then I'll describe some recent progress in higher dimensions with some reminiscent ideas of this story about which there was lots of work recently. So I have quite a bit to do today, and also it's Friday 13th, so what can go wrong, right? So let's see where I get. Are there any questions about the topics we've discussed yesterday? Okay, the first comment I wanted to make is about the symmetry enhancement here. I just wanted to clarify a little bit. There was a question about so this Wezumino-Witten model that arises here in the infrared has a higher symmetry than the SO3 symmetry that's manifest microscopically. So I just wanted to clarify what is the exact symmetry enhancement pattern here. So I'll just make a short comment now about this Wezumino-Witten model phase at the negative mask word. So when we have a Wezumino model for gauge group SU2, our variable is some SU2 matrix G. And the symmetries act by left and right multiplication by different SU2 matrices. So the symmetry would appear to be SU2 times SU2. However, one has to be again careful about this center of SU2, which may act trivially. And indeed, you see that if you act with the center from the left, it can be cancelled by the action of the center of the other SU2 from the right. And therefore, the true symmetry of this model is in fact SU2 times SU2 mod Z2, which is also known as SO4. Okay? So the symmetry enhancement that we're talking about here, let me just write it here. So the symmetry enhancement that's going on here is a SO3 enhancing to SO4, which is reminiscent of some recent discussions about antiferromagnets in 4 dimensions, in 2+1 dimensions, where people propose similar symmetry enhancement mechanisms in higher dimensional antiferromagnets, quantum antiferromagnets. So that's one comment, that this is there is some interesting symmetry enhancement at the fixed point from SO3 to SO4. And this can perhaps be also true in higher dimensions in some constructions. That's comment number 1. And so now let's get to the beef of what I wanted to tell you, which is how do we prove, we had the satisfactory proof on the lattice that there is no gap in the continuum limit, but now I would like to show you that there is a very nice also proof in the continuum, which is in fact technically much less heavy and much easier to repeat in higher dimensions. So that's the main first topic I would like to discuss. So instead of just telling you the answer, I wanted to start with some little bit of intuition of because you see, if you like 5 years ago you would have told somebody that this model has an anomaly, it would be somewhat mysterious because there are no fermions. Okay, so there are no anomalies of the ordinary kind, but there are more exotic discrete anomalies. And it's true that they exist, and they are almost as powerful as continuous anomalies, and there is therefore no reason not to study them in as much detail as the continuous anomalies. You will see that the consequences for the anomalies that we will derive in this model will be to prove that there is no trivial gapped phase, even in the strongly coupled regime. You need to have either symmetry breaking or the Wezumino-Witten model.
Clarification?
Yes?
The lambda phi squared term
Yeah. That's why I put like this additional parenthesis here.
Okay.
So the sum over I is within the parenthesis, so that the symmetry is not broken by the potential. The SO3 symmetry is not broken by the potential. For that, you need to perform the sum inside the parenthesis.
So, but then I'm just asking because then the symmetry is SO4 of that term specifically.
That's right, but there is a gauge field that couples to these guys and breaks the symmetry to SU2, and in fact to SO3.
Okay, but just that term is SO4 in there.
Yes. See, I just wanted to make one comment because it's, this is a comment that I made following Slava's question yesterday. So Slava, I just wanted to, you asked that after the lecture. I think the symmetry here is SO4 in the Wesovino model. So the symmetry enhancement is that, from SO3 to SO4. Okay, so there are no fermions, but we can still prove something rather spectacular about the continuum limit, about this quantum field theory. So now I'll start with some intuition. I assume that most of you have not seen such a thing before, so I'll start with some intuitive explanation of why can we do something like that. So we are going to analyze this phase of the model in some detail. This very weakly coupled phase where the mass is huge and positive. So we're going to analyze this phase in some detail, in a little bit more detail than we did yesterday. And we'll see that something rather amusing is happening. So we have two vacua. This phase is described basically by free U1 gauge field in 1 + 1 dimensions. It's a topological, free gauge fields in 1 + 1 dimensions don't have any degrees of freedom. So all you gotta do is to choose the electric field. It's just a constant electric field, it cannot fluctuate. So the two vacua correspond to electric field plus minus a half. So here the electric field is just positive a half, and here it's negative a half. And these are two superselection sectors that are exactly degenerate at theta equals pi. In fact, they are protected by charge conjugation symmetry. So the first hint that something amusing is happening comes from constructing. So imagine that you are a lattice person, and you insist that this is your space, X, okay? And you could easily insist that at minus infinity you sit in that vacuum, and at plus infinity you sit in this vacuum. It's a very easy thing to arrange on the lattice. And so the electric field here would be plus a half. Let's say that plus a half goes inwards. And from here, it would be minus a half. Minus a half, okay? So how would the system minimize the energy eventually? Well, you need to use the massive particles that have a huge mass m to interpolate between electric field minus a half and electric field plus a half. So how do we, does anybody have a suggestion? How do we interpolate between minus a half and plus a half? What do we need to put in the middle? With charge 1, right? But we have two of them. We have phi 1 and phi 2. So we can put either phi 1 or we can put phi 2. Okay? So if you were to study this configuration on the lattice, you would find that it's doubly degenerate. There are two charged particles that you can put here. So there is like a Hilbert space that is reminiscent of the up-down Hilbert space at the domain wall. So the domain wall has a twofold, let me just write it. DW stands for domain wall, or a kink. It's the same. It's just a better generalization to higher dimensions. The domain wall has twofold degeneracy. Now, this is already somewhat atypical. So oftentimes, the domain walls do not carry interesting quantum numbers. But in this case, it's twofold degenerate. Is it clear why? It's twofold degenerate. Furthermore, it's deconfined. Let me explain this word deconfined. Let's go to the previous vacuum. Let's say that we were in the plus a half vacuum. Let me just draw a picture, and then I'll leave this blackboard. Let me explain what does the word deconfined means. Suppose you were in the plus a half vacuum. So the electric field is a half everywhere. So in particular, it's a half at far infinity, both at minus infinity and at plus infinity. The electric field is plus a half. Suppose you wanted to ask how much energy is it going to cost me to excite one of those particles phi, like we did just a second ago. So if we were to put, like, say, phi 1 here, what would happen to the electric field? It would have to flip. So the electric field here would have to be -0.5. But we're stuck because the asymptotic boundary conditions are fixed by the lattice person, and he would not agree to change them. So that would cost infinite energy, unless you put another phi with the opposite charge, and then you could jump back. So if you try to put a single phi in the usual vacuum, it's confined. It's like a quark. You cannot release it. It costs infinite energy to put a single phi. But you can put two phis, and then they're connected by a string. However, if the boundary conditions are like that, then they can move. You can put them wherever you want. It doesn't cost any energy. In fact, you need to put them. That's the minimal energy configuration. You need to put a single phi without phi dagger. So it's like we release the quark. So this is like quark deconfinement, okay? That's why it's called deconfinement, because it's like we've deconfined the phi fields. So people say, the nomenclature is that people say that the domain wall has deconfined phis, deconfined charges. And it's twofold degenerate. That's very simple semi-classics.
In the case of normal boundary conditions, the distance between two charges would be arbitrary, right?
Yes.
Potential.
Yes.
So this is also a sign of deconfinement?
So you have to put two. Yes, you have to put a plus and you have to put a minus. And the electric field between is going to be a half, let's say, but here it's a half in this direction. So you can change the distance between these two guys without paying any fine. Yes. But you have to have two of them. Whoa, what just happened? Oh. Okay, so the question is, let us be more careful about the quantum numbers of the kink, of this kink object. What are the quantum numbers of the kink? So while all the local operators were SL3, were charged under SL3, were in SL3 multiplets. So if you are a Bootstrap person, you were to try to bootstrap this model, the symmetry would be declared to be SL3. In SL3 multiplets, we see that the domain wall theory is not in an SL3 multiplet, right? The domain wall is in a doublet of SU2, and SU2 is the double cover of SL3. So the domain wall, strictly speaking, is not in an SL3 representation. If you want to be sophisticated, and that's actually a good remark to make at this point, you could say that it's in a projective SL3 representation. So it's almost an SL3 representation, but it's not quite true. So it's a projective SL3 representation. Projective SO3 means that there is a central extension of SO3 under which this domain wall degrees of freedom transform, and the content is the same as what I said here. You could say these words instead. So this is another sign of deconfinement, because the difference between SO3 and SU2 is this Z2 gauge transformation. And in some sense, the Z2 gauge transformations The Z2 gauge transformation acts on the physical Hilbert space. So that would be really the physical Hilbert space at infinite space. And the physical Hilbert space would transform under the gauge symmetry. So it's not neutral under the gauge symmetry. It would be in a representation of SU2 rather than SL3. Okay, now let me draw an analogy with the antiferromagnet. And you would see that this domain wall, you remember that perhaps yesterday, Slava complained that SU2, the symmetry of the antiferromagnetic model is not the same as SL3, or maybe somebody else made this comment. So now we see that the resolution is perhaps that a single spin on the antiferromagnet maps to the domain wall. Let's see if this is correct. Let's see if indeed a single spin is confined. Perhaps a single spin is confined also on an antiferromagnet. Okay? And then this would really make sense. That would further imply the charge conjugation symmetry is the same as a translation on the lattice, which we'll see now. So let's establish this funny correspondence, that the translation on the lattice becomes a unitary, becomes an internal symmetry in space-time, in the continuum, and the single degree of freedom S, which is gauge invariant, becomes the domain wall. So let's try to establish this qualitative correspondence. That's actually, and then I'll try to tell, I'll give you a quick proof of a theorem that says that this must be true, that some space-time symmetries on the lattice must become unitary non-space-time symmetries in the continuum limit in a huge class of models. So this is not an accident. So let's see why. Let's think about classical antiferromagnets. Okay, classical antiferromagnets. So classical antiferromagnets may have roughly speaking, two degenerate states, which are this and this. What do they differ by? A translation you can get from this to this by a translation by 1 unit, right? So translating the antiferromagnet by 1 unit is going from this vacuum to this vacuum. And the analogy is that this is the electric field a half, and this is the electric field minus a half states. And in fact, the single spin is like a domain wall. So how do we construct a configuration? Suppose you're a lattice person, and you have a huge, huge spin chain. Okay, we have a huge, huge spin chain. And you're free to put whatever boundary conditions you like. So you like that at the far left, you will have this antiferromagnet that, where the ups are the odd spins. The odd lattice sites are populated by ups. And very, very far up, so I need to draw it. So this would be up, down, up, down, up. But very, very far here, you want to start from down. You just insist that that's true. So now the antiferromagnet has to find the minimal lowest lying configuration, but it's stuck, right? You need to minimize the energy. You have to pay a little bit. You have to choose either this or this. It's the same energy, right? The antiferromagnet cannot be in one of those configurations because you translate it by 1 unit asymptotically. So it has to fill the gap by putting up or down. So you have a 2-dimensional Hilbert space. So if we impose these boundary conditions on an antiferromagnet, like on the lattice, we would find the same picture, exactly the same picture. So that implies the translations is the same as charge conjugation. The domain wall theory is the same as the spin a half degree of freedom. And that's why the spin a half degree of freedom, even though it's a local operator in the lattice, it's better interpreted as a domain wall in the continuum limit, and it's not a local operator. It does not act within a superselection sector. It takes you from one superselection sector to another superselection sector.
Can you say again, what is the mass parameter on in the spin chain description?
It was 1, but you could put some J.
Sorry, I mean the mass parameter, the M squared you tune to go from these different faces, because before you're talking about the one on the other face, M squared less than 0.
Right, I'm talking now about this phase where M squared is positive and huge. So this is going to cost you M squared compared to the vacuum.
I'm just asking in the spin chain Hamiltonian, what is the operator that would, what's the information that would take you from to this phase?
In the spin Hamiltonian, we just had this. So just think about it classically for a second. So if you were able to arrange for this configuration, the energy would be, let's say, minus J.
No, but I thought that Hamiltonian describes the M squared less than 0 phase.
Right. But you could, I mean, but the picture is correct regardless of the Hamiltonian. You can add these kind of terms if you want to really be.
So it's some generic term.
Yes, like some generic term that does not violate Frobenius-Perron, and you jump into a phase where there is a twofold degeneracy and translational symmetry is spontaneous. Yeah, thanks for the comment. But the picture is always the same. In the conformal phase, if you really do the analysis carefully, this would be like a gapless mode, and it won't be. The domain wall tension would not be finite. So this picture, in the critical point, this picture becomes like this, and the domain wall theory has zero tension, so it's like a spin-on. But you can jump to the phase where it's like a domain wall, and the gap is finite, and then this picture arises. Very good.
So this T going to charge conjugation is kind of an order of limits issue.
Say again. T squared is a translation. So T goes to a charge conjugation, but T squared goes to a translation in the continuum.
So this translates by like 0 because you're in
Yes, yes. It's an infinitesimal translation, so it's the momentum. Yeah. So this is funny. It's like the charge conjugation is the square root of momentum, but there is no sense in which this is true in the continuum. It's true on the lattice. Yes, exactly. T squared maps to translations in the continuum, but T maps to charge conjugation, which is bizarre. Let me tell you why this has to be true in any system like that. What I haven't proven yet, but I'm on the way of proving, is that this continuum field theory has an anomaly. What is an anomaly? An anomaly is an obstruction to gauging all the symmetries. I'm just being a little bit quick just to answer your question, so it might be too advanced for the rest. So the symmetries of this model are like O3, and I'm saying you cannot gauge O3. I'll prove it soon. That means that some subgroup of O3 cannot be on site on the lattice. So some subgroup of O3 must act as a translational symmetry on the lattice. Why? If the whole O3 symmetry was visible on site on the lattice, I could gauge it trivially. I would just add links that transform in O3, and I'm done. So any quantum field theory that has an anomaly in the continuum, if you want to be able to see the symmetries on the lattice, some of them must be embedded in space-time symmetries on the lattice. And then you cannot gauge it. Secretly, you cannot gauge the whole O3 symmetry on the lattice because one of them is a translational symmetry, and it's kind of hard to imagine how you would gauge it on the lattice. You need to add gravity or something on the lattice. So it's not clear what does it mean. But this is extremely general. If there is an anomaly in the continuum, there cannot be a realization of all the symmetries on site. Lattice people who try to simulate QCD have been battling with this for 30 years. The reason that you cannot construct massless wild fermions on the lattice is because there is a 't Hooft anomaly in the continuum. That's it. It's the same thing. And in fact, one of the most common solutions to this issue is to put domain walls in 5 dimensions, which is very similar to making the axial symmetry into a space-time symmetry. So somehow our community did not appreciate this very.
Your comment does not apply to QCD.
QCD. Well, I just made a comment because it's too advanced for most people, but I just said that this is an extremely general issue, and the reason that people cannot construct massless QCD on the lattice, obeying the axial symmetry, is because it has a 't Hooft anomaly. That's it.
You can construct massless QCD on the lattice because you can fine-tune. There's a mass parameter. You cannot construct a manifest.
Manifest. Yeah, manifest. You cannot have all the symmetries manifest. You need to fine-tune. But here they have all the symmetries manifest, except that one of them is a space-time symmetry. That's another way to do it. You can either try to fine-tune and be lucky, which is what people on the lattice have been doing all along, or you can try to make one of the symmetries a space-time symmetry, which is much more interesting and has not been much explored in the context of high-energy physics. But it's all over the place in antiferromagnets. Okay. So now I want to now get to the continuum argument of why there is an anomaly. So even though I'm concentrating on 2 dimensions and the CFT that we find here is boring, like from the Bootstrap point of view, it has been solved 100 years ago, this SU2 level 1. The ideas are completely general and they apply in 3D. And in fact, last year in Sao Paulo, I explained the 3D model that obeys exactly the same properties. So the zoo of 3D models that people have recently constructed are all based on these ideas. So you just need to understand the 2D case and you're good. So the next question that we would like to address is the continuum question. So, where was that? Yeah, OK. So I'll just discuss within this blackboard. So we found that in the continuum, in the QFT, we found that the domain wall has twofold degeneracy. The first question that we would like to address is whether this degeneracy is non-perturbative. We see this degeneracy with like naked eye in this semi-classical limit. But who said that who said that these are exactly degenerate? How do we know that these are exactly degenerate? So the first simple claim is that this is non-perturbatively true. So the domain wall does have 2 states. And this is true in the full non-perturbative theory. And the argument is trivial. I mean, the argument is that since it's an SL3 representation, as projective SL3 representation, it cannot disappear. Like if there was some, small splitting, what would you do? What would be the quantum numbers that you would assign to the 1 degree of freedom that's left? Doesn't make any sense. So this must be non-perturbatively true because it's an SL3 projective representation. So this is not an artifact of the classical limit. It's non-perturbatively true. OK, are there any questions about it? Now the next step. The next step involves trying to prove that either charge conjugation is broken in the bulk, not on the wall, like in the full theory. So this is the theorem that we'll try to prove. Theorem: either C is broken or either C is broken or it's gapless. So this is the theorem that I want to prove now. That means that, well, that rules out the existence of a trivial phase somewhere in the phase diagram. And here the argument is extremely quick, but unfortunately, I don't know how to present it without going into some math. And so I'll try to give you an intuitive picture, and then I'll write the formula, and you'll try to understand it maybe later. The arguments that you would see in the literature are a little bit sloppy. People say that since there is the confined criticality, you cannot go to a gap phase. But it's kind of a circular argument because you need to have these 2 states in the first place, to have a domain wall. And it's not an excellent argument. So the argument that I'm going to try to give you, so this was a plus a half, and this was minus a half. So an anomaly, what is an anomaly? Let's define a quantum anomaly. A quantum anomaly is the inability to couple the symmetries to gauge fields. Okay, so when you try to gauge the symmetries, you find that the partition function is not gauge invariant. under some gauge. And it could even be discrete gauge fields. It doesn't have to be continuous gauge fields. This idea is general. So it applies to both discrete and continuous symmetries. OK, so the best way to understand why there is an obstruction in this model is to start from this phase and go back for a second to our picture of the domain wall. So we have this phi 1 and phi 2. Let me just make a general comment. Ordinarily, to establish that there is an anomaly, we do a one-loop computation. You remember this kind of computation. Or in 4 dimensions, we would do a computation like this. But this is good for continuous anomalies. For discrete anomalies, you cannot do Feynman diagrams. You have to appeal to more abstract arguments because the nature of these issues is discrete. As you have seen in the Lattice model, it's all about some translation by one unit. It's a discrete issue. So you cannot compute it just in, from a one-loop diagram. You have to appeal to more abstract and sophisticated ideas. And oftentimes, it's even hard to compute it. So you have to rely on some tricks. So the argument is going to start from this phase. So this vacuum, which was the electric field half, is related to this vacuum, which is a minus a half by charge conjugation. And then we have this deconfined doublet of quarks on the wall. So here is going to become just a tiny bit sketchy. So you remember, I want to appeal to some analogy. Just to appeal to some analogy, and then I'll give you the precise mathematical argument for those of you who know a little bit about fiber bundles. So the analogy is the following. You remember that when we studied U1 Maxwell, we had 2 options, theta equals 0 and theta equals pi, that we distinguished. Theta equals pi had 2 ground states, which were like electric field a half and electric field minus a half. While theta equals 0 had 1 ground state where the electric field was just 0. So theta equals pi means, in quotation marks, that there is a half integer charge. That's the analogy. So there is, in some sense, a half integer charge. So while the gauge field is a U1 gauge field, this is just ordinary Maxwell U1. So while the gauge symmetry is U1, in some sense, theta equals pi behaves as if somebody put a half integer charge at infinity, because the electric field is a half or minus a half. Okay, that's an analogy that I would like to appeal to. So now we go to this picture, and we try to gauge SO3. So this is just, suppose we would try to gauge SO3. And that's, at the level of the Lagrangian, that's straightforward. You just take all the covariant derivatives, promote them to SO3. You add an SO3 gauge field, and you couple that to the phi fields. So that would be straightforward at the level of the Lagrangian. But let's see whether something would go wrong if we were to gauge SO3. So the issue is that there is a half integer charge. The main idea is to think about this doublet of SU2 as a half integer charge in terms of SO3. Okay? Is the analogy more or less clear? In some, Somebody said no. I can try to explain it again. You said no? Who said no?
I said no.
Good. So why? Okay. This I understood. Good. So in what sense is an SU2 doublet a half integer charge of SO3? The mathematical sense is that if you go to the double cover of SO3, then it's a representation. In the same sense as here, if you go to the double cover of U1, then a half integer charge is fine. So the idea is that this is like a half integer charge for SO3 gauge fields. So suppose we had SO3 gauge fields in the system. So because we have a half integer charge, in some sense, the SO3 action would have here theta equals pi. So there is some theta angle for SO3 gauge fields. And on one side, there will be a theta equals pi for that SO3 gauge field. But on the other side, theta will be 0, because we have a half integer charge for SO3. So the main thing that I'm going to prove now is that SO3 has a theta angle. SO3 gauge fields have a theta angle. And because of this structure of the domain wall, the theta angle here is pi, while here it's 0. Okay, because we have a half integer charge for SO3. The only thing that you are not seeing yet is that SO3 gauge theory has a theta angle. You don't know how to write it because you just cannot. You cannot write it like this because this transforms in the adjoint of SO3. So the only thing that you are missing to see this argument is that you don't know how to write an SO3 theta term. But that's something that I'm going to explain. Just accept for a second that there is an SO3 theta term. Then this becomes more or less clear. That there must be theta equals pi on this side and theta equals 0 on this side because we have a half integer charge for SO3. But now, charge conjugation is broken because theta equals 0 and theta equals pi are not related by charge conjugation anymore. So what we've seen is that if we gauged SO3, charge conjugation would be broken and vice versa. So it's impossible to gauge all the symmetries in a consistent fashion. If you gauge the SO3, charge conjugation is explicitly broken. That's the essence of the argument, and now I'll fill the mathematical details. I'll give you the precise mathematical argument. So, in the domain wall configuration, we have two vacua. So here theta of SO3 would be pi, and here theta of SO3 would be 0. Remember that the theta of the U1 is always pi. We're discussing the system where theta of the U1 is pi. This is just an auxiliary thing that I've introduced to prove a theorem. This doesn't really exist. And therefore, charge conjugation is explicitly broken. So these two vacua are no longer related by charge conjugation symmetry because theta equals pi goes to minus pi, so it goes to itself. It doesn't go to 0. So it's explicitly broken in the presence of SO3 gauge fields. In the presence of SO3 gauge fields. And that means that you cannot gauge all the symmetries simultaneously. And that means that O3, which is charge conjugation SO3 times SO3, this cannot be gauged, and therefore there cannot be a trivial ground state. Why there cannot be a trivial ground state? Because if there was a trivial ground state, you could couple it to SO3 gauge fields with, easily, trivially, and that's it. But the partition function must obey this property that when you perform a charge conjugation, you generate a theta equals pi for SO3. And that could not be obeyed if there are no massless fields or no symmetry breaking. You need some low energy dynamics in order for the system to generate this interesting response function. That if you act with charge conjugation, you generate a theta angle for SO3. This cannot be done without there being massless fields or gapless states. Or sorry, something gapless in the continuum, which could be either due to spontaneous discrete symmetry breaking or due to a genuine CFT. So the two logical options is breaking of C or gapless. This completely rules out the possibility of a trivial gap state, like in the theta equals 0 model. Yes?
How do we know how charge conjugation acts on these SO3 gauge fields?
Just because it acts like you would imagine. I'm appealing to some analogy here. Charge conjugation reverses theta, basically. Yeah.
Why couldn't the SO3 be broken?
SO3 is an auxiliary object. It's not dynamical. It's not fluctuating. SO3 is like a classical gauge field that I've put in. And what I argued is that in this vacuum, it has to be pi, while in this vacuum, it has to be 0. And therefore, once you have SO3 classical gauge fields, you cannot gauge charge conjugation anymore because it's not a symmetry anymore.
No, I'm asking, before we put in the gauge fields, we had the O3 symmetry.
Yes.
And either C or SO3 could have been broken.
No, SO3 cannot be broken. That's why the two options here are either breaking of C or a gapless state, namely a CFT. Because SO3 cannot be broken in 1 + 1 dimensions.
Oh, okay. Yeah.
The analog, if you were to apply such an argument in higher dimensions, there would be 3 logical options. Let's say breaking of C, breaking of SO3, or a non-trivial CFT.
It's because of this Coleman-Mermin theorem.
It's because of the Coleman theorem. Yes?
Can you explain a bit better this argument that if O3 cannot be
Good. I'll explain it now.
I can explain why it's not difficult.
Yes?
I can see many systems which float a gap phase,
Yes?
and I see by inspection that they can be gauged, but I don't know how to reverse this argument.
Okay. I'll try to. This is a crucial. Yeah. So I'll do first the argument of why. Let's say I'll do an abstract argument of why, if a symmetry cannot be gauged, then it cannot float to a trivial state, and then I will explain what is a theta angle for SO3, filling up the mathematical gap that I have left here. Yeah. Yeah, we did this computation of the anomaly in the massive phase. So it's extremely hard to compute the anomaly. It's hard to compute the anomaly in the SU2 level 1 Wazumino-Witten model, but it's possible. People have done it. The anomaly is independent of the mass. So oftentimes, these anomalies are extremely hard to compute. And you have to find a way to deform the system while preserving all the symmetries to a phase where you can do something. And this model, the reason I presented it is that in this charge conjugation breaking phase, I can make an argument without much difficulty. But if I was stuck in the SU2 level 1 phase, I would have to now start computing partition functions of some CFT, trying to couple it to discrete gauge fields, and it would be much, much harder. So oftentimes, we don't know how to compute these anomalies directly. So we try to find a relatively simple vacuum while preserving all the symmetries and making only continuous normalizable deformations. So that's the trick in this business. You have to try to find a deformation that works. We don't know how to compute them from first. We don't know how to compute them otherwise. Yeah.
Sorry, could you explain again why when charge conjugation is preserved, you must have a CFT?
Because SO3 symmetry cannot be broken in 1+1 dimensions because of Coleman's theorem.
No, I mean, yeah, assuming that, but you said something like you must have zero modes to generate a response.
That's what I'm going to explain now. I was asked to. Okay. So suppose you have any abstract system with symmetry G, that you should think about the discrete symmetry or a continuous symmetry. It doesn't matter. So we have some symmetry G, and suppose that it cannot be gauged. So the question is, why does that mean? So suppose it cannot be gauged. So the consequence of that is that the long distance limit, the infrared, has to be non-trivial. Okay. So what is the argument? The argument is by contradiction. The argument is by contradiction in the following way. Suppose there was a trivial gapped vacuum. So a single vacuum, and all the particles are massive. Okay? We start from some continuum theory, and we assume that there are some massive particles, and the vacuum is unique and trivial, and there is nothing else going on. So now we couple the partition function to the gauge fields, A mu. So these gauge fields could be discrete, but it won't matter for the argument. So we do like a response theory. We couple the gauge fields to, we couple the symmetries to classical gauge fields. These are classical, not fluctuating. And therefore, the partition function can be viewed as a function of those. So you can think about this partition function as a generating functional for correlation functions of the currents or the charges or something. So this object exists. Okay? What do we know about this object if the system is completely gapped? So what we know about this object is that it's an exponential of a local Lagrangian that depends on A classical. So this is the main issue. This is the main idea, that if the system is gapped, the partition function must be an exponential of a local gauge invariant, a local gauge invariant, a local function of A mu. I'm not going to say it's gauge invariant yet, just a local function. So something that depends just on nearest neighbors or something like that. What is local is a complicated question that I can address, but this is the crude picture. Is this clear? Why this has to be true? The idea here is that if let's say if all the momentum space propagators have like a mass, you can expand everything around p equals 0, and you only get analytic functions. You need something massless, so that there are some singularities in momentum space in order to get non-analytic functions at low energies. So this is the low energy A. This is the low energy, a representation of the partition function. You've integrated out all the massive particles. Everything is on exponentially small scales. Like all the particles can only propagate on exponentially small scales. Well, on scales that are like 1 over the mass. And therefore, you cannot generate something that is singular at long distances. So it has to be a local function.
What is the equivalent statement for discrete gauge symmetry?
For discrete gauge symmetries, the difficulty here is that you have to tell me what is local. But people have developed a whole theory of classifying what terms, which functionals are to be deemed local and which functionals are not to be deemed local. Okay? There's a whole theory. It's very clear. It's completely classified.
Is discrete Wilson line a local function or not?
Discrete Wilson line?
Yeah.
No. Intuitively, clearly no, right? Yeah. If to evaluate this Lagrangian, you need to know A everywhere at the same time, then it's not A. So local is something that like you should intuitively, for discrete gauge symmetries, you have to do quite a bit of work trying to mathematically define what it means to be local, but people have done that. If you want to learn about this, you want to learn about this classification, the keyword is invertible theory. So the way local Lagrangians nowadays are often called invertible theories. Local Lagrangians for classical sources are called invertible theories. So if you want to learn about the classification of what is deemed local, this is the keyword. Okay, so now imagine, however, that there is an anomaly. So somebody told you that it cannot be gauged. So that means that the variation of the partition function under some gauge transformation alpha has to be given by an exponential of something. So this is the exponential of the anomaly, which is a function of alpha and A. So this is what an anomaly means. An anomaly means that the statement of an anomaly is that the variation of the partition function under some gauge transformation is given by some local functional. So there are two local functionals. One is the one that you get from integrating out all the massive stuff, and the other is the equation for the anomaly that says that under a gauge transformation, you should generate this. Okay, so an anomaly, so we say that the system has a genuine anomaly if this functional is such that it can never be obtained from a local functional. So this is a definition of an anomaly. If delta alpha of L local is not equal to L anomaly alpha A, this is a function of A, for any L local, okay, if this is true, then we've disallowed the trivial phase. We've ruled out the trivial phase. Then the theory cannot be trivial. And that's it. So an anomaly is not defined just by saying that the partition function is not invariant. You have to add the cost cycle condition, that it's not a variation of something local. Okay? So this is like how you prove that if there is an anomaly, you have to just do a little bit of work to see that it's not the variation of a local Lagrangian, and then you're done. And local Lagrangians are classified, so we know what it means for a Lagrangian to be local. Okay, so are there any questions about this argument? So the reverse argument is clear. it's less clear what it implies. So it implies the complement of the theory being trivial. What is the complement of the theory being trivial? You have to have either more than one vacuum, or there must be massless particles. Okay? That even having just more than one vacuum is enough for this Lagrangian to be not strictly local, because when you've integrated out the massive fields, you were stuck in one superselection sector, and that's not quite right. Your effective field theory doesn't capture the fact that there are two superselection sectors. So oftentimes, just having more than one superselection sector is already enough to generate sufficient non-locality in this thing so as to be able to generate an anomaly. And this spin chain is an example, because there is a phase where there are two superselection sectors and it matches the anomaly. It's only when you have really just one superselection sector with a gapped spectrum that this is true.
Your previous argument was formulated in pretty different terms, right? So you say you could rephrase everything in terms of the anomaly.
Now I'm going to do it. I'm going to define I'm going to tell you what is L anomaly, so that you could, if you are interested in the subject, you could learn you could learn about it a little bit more. So first, I have to tell you what is a theta angle for SO3. A famous fact in many high-energy physics applications, for example, if you ever looked at Seiberg-Witten theory, Donaldson theory, also in some applications in condensed matter physics, is that SO3 gauge theory has a theta term, but it cannot be written using ordinary gauge fields, because you cannot just write trace of the A, because A is an anti-symmetric matrix. So this doesn't make sense. So instead, there is an object which you may or may not put. So there is an object that is called W2 of SO3. I'll explain which you can integrate over any two manifold. And you can put it in the action with either coefficient 1 in some normalization or with coefficient 0. So SO3 gauge theory doesn't really have a continuous theta angle. It has a discrete theta angle. It's either 0 or 1. So when I drew that picture somewhere where there was an SO3 theta angle in one of the vacua, here, they're up there. So it's not like it's 0 or pi and you can do anything in between. It's either 0 or pi. There's nothing in between. You cannot write something in between. So what is this? So we'll be studying the situation where this is 1. This is a theta angle for SO3 gauge theory. And what is and you can integrate this. You can integrate this discrete object against any two cycle, and it's a local thing. It's considered to be a local Lagrangian, even though we cannot write it using the elementary gauge fields. It's considered local. So this is considered local.
You mean e to the 2 pi I times this inserting into passing rule?
Yes. So we just put e to the, let's say, well, pi I is a sensible convention. So what does it mean? I want to tell you what it means in terms that you can actually understand a little bit more. So we have a two-cycle M2. So this is called the Stiefel-Whitney class. W2 is called the second Stiefel-Whitney class. So what does it mean? So mathematically, it means that if you have some two manifold M2 and you have some SO3 bundle, we put an SO3 bundle on this manifold, there is a question of whether this bundle can be lifted to an SU2 bundle. And it's either yes or no. So if W2 integrated over this cycle is 1, then you cannot lift that bundle to SU2. If it can, then you can lift that bundle to SU2. If you're familiar with the twisted boundary conditions of a 't Hooft, that would be like so if W2 is 1, if this is 1, then it means that we're putting twisted SU2 boundary conditions. Twisted SU2 boundary conditions. So this is no longer an SU2 bundle, but it's an SO3 bundle. If you've ever seen the construction of a 't Hooft of twisted boundary conditions, then this is exactly that. So I'm not going to explain in much more detail what it means. I'll just write the key formula. the key formula is that our semi-classical considerations have proven that if we take charge conjugation and act on the partition function, which is some function of SO3 gauge fields. So this particular anomaly is simple. We don't need to make all the symmetries. We don't need to couple all the symmetries to gauge fields. It's already visible when we just act with a global symmetry on the partition function, which is a function of SO3 gauge fields. So the statement is that this goes back to itself, but not quite. We pick up an exponential of I pi W2 of SO3. So this is, in this way, this looks a lot like the 't Hooft anomalies you've seen in school, in graduate school. You remember that the usual chiral anomaly looks exactly the same. We say that delta alpha z is z up to an exponential of f wedge f. This is the usual chiral anomaly with some parameter alpha. So this is exactly the same, except that f wedge f is replaced by some slightly more advanced beast, which is this discrete invariant. But it's exactly the same as a continuous anomaly. How did I prove that this exists? Well, I didn't do some deep complicated computation. What I did was to go to this symmetry breaking phase and argue that on one side you have to have theta equals pi. For the SO3 gauge fields on the other side you do not, and therefore charge conjugation symmetry is not a symmetry if SO3 gauge fields exist. So you see that if you couple the system to SO3 gauge fields, charge conjugation symmetry is not a symmetry anymore. It does not leave the action invariant, does not leave the partition function invariant. So this is enough to prove that either C is broken or it's safety. Either or. Okay. Now, the last 5 minutes, I'm just going to tell you quickly that so I'll make just some laundry list of examples in higher dimensions, which have very similar properties, where you can prove these strong theorems quite easily. Yeah.
So this argument you're giving here seems to be more complicated than just in SU2 level 1 W7 model.
Possibly, but you need, well, let me tell you, in this, I think you're right. Let me tell you why. Can I just tell you why I think in this particular case you would be right? So SO3 that is visible microscopically is enhanced to SO4 in this WCW model. But we also have charge conjugation symmetry. Charge conjugation is like the matrix -1, -1, -1, because together they make up O3. But this matrix can be easily embedded into SO4 by putting another minus. So the O3 symmetry that we had microscopically is embedded inside SO4. And therefore, to compute this anomaly in the West-Zumino-Witten model, it would have been enough to couple the system to SO4 gauge fields. So so you don't need to invoke like external discrete symmetries. Like the SO4 symmetry is enough. You could have worried that perhaps you need also the symmetry that exchanges the two SU2s, but it's not necessary. So perhaps in this example you would be right.
I was thinking of something much simpler. This W7 model in this case is just a free boson and self-free radius. And
Okay.
this charge conjugation symmetry is basically duality.
Yes.
And this triple anomaly is basically this cycle that's actually in Komargodski. So.
Yes, I agree. It's the fact that there is an anomaly involving T-duality at the self-dual radius. I agree. Good. So now I'll just make a quick laundry list. Yes.
Can you perhaps explain a bit better why this is considered a local term that you can add to path integral?
This W2.
What is the criteria?
The criteria is that it's the criteria of what is deemed local is whatever can be generated from a trivial gapped phase. That's what's considered to be local. That's the definition of an invertible phase. So to convince you that this funny thing is really local, I have to give you an example of a trivially gapped Hamiltonian which generates that. And this is easy to do. You just take the model that we discussed, but you take theta equals 2 pi. So theta equals 0 and theta equals pi are exactly the same. But if you couple the system to SO3 gauge fields, one generates this contact term for the background gauge fields, and one does not. is this acceptable more or less as an argument? Suppose this was true. Would that be acceptable? Yeah. So I can quickly give you a proof that this happens. Maybe instead of going over the laundry list in higher dimensions where this is true, I'll explain why this, for the more advanced people in the audience, I'll explain how to see that. So this is I would like to just focus for a second on this term that we've added to our Lagrangian. This is the U1 theta angle term, okay? So the gauge symmetry was U1. This was our gauge symmetry. So we can put it in brackets. And our global symmetry was SU2 mod Z2, because the Z2 was already in the gauge symmetry. But suppose we couple these two gauge fields. So now we think about all the gauge fields on the same footing. What is the gauge symmetry of the full system? So the gauge symmetry is going to be U1 times SU2 mod Z2. This is U2. So if we actually couple the system to SO3 gauge fields, the whole thing would be a U2 gauge theory. And if this is gauged and this is considered like classical, we get SO3. So that's how you see it. So this would be the full gauge symmetry under which phi would transform. Our elementary fields phi would transform. An interesting fact about U2 gauge theories is that if you now construct this trace dA, so this becomes that. This now becomes the trace of dA. This is how the U1 is embedded in U2. And we need to put I theta over 2 pi. An interesting and known fact about U2 bundles is that the trace of dA is no longer an integer, but it's actually 2 pi z over 2. So when you couple the system to SO3 gauge fields, the periodicity of the theta angle is effectively enlarged from 2 pi to 4 pi. So theta is now in the interval 0, 4 pi. So this is one way to see this anomaly, which does not involve complicated computations or going to the massive phase. You just have to realize that in the presence of SO3 gauge fields, the periodicity of the theta angle is enlarged from 2 pi to 4 pi. And therefore, the point theta equals pi is no longer invariant under charge conjugation, because pi and minus pi are no longer the same. And the difference is exactly, so there is a mathematical invariant, which measures whether the U2 bundle has integer fluxes or half integer fluxes. And that mathematical invariant is exactly W2 of SO3. So that means that the difference between the theta equals 0 theory and the theta equals 2 pi theory is W2 of SO3. But the theta equals 2 pi theory is gapped and trivial, so therefore it must generate that term. But this is the quickest argument to see the anomaly. If you knew that U2 bundles have a twice bigger range for theta because of this half integer, you would immediately know that charge conjugation is not a symmetry at theta equals pi in the presence of SO3 gauge fields. And that's it. So the argument is really just a few lines, but it's mathematically sophisticated. And you can repeat the same idea in many other systems. OK, so I ran out of time. If you want to see examples in higher dimensions, you can look at the video lectures from last year, I guess, about 3-dimensional, 2 plus 1-dimensional examples of such things. Oh, I do have 10 minutes. I thought I ran out of time. Do I have 10 minutes? OK, I'll just do a quick review in that case. I'll just do a quick review of 2 plus 1D. This is not going to be nearly pedagogical, but I'll just mention a few examples that are very interesting. One is QED 3. This is an example that has received a lot of recent attention from Bootstrap, Lattice, and people like me. The microscopic symmetry. So let me just write the model. We're talking about 2 plus 1 dimensions. So the model is f squared plus d psi dagger. So this is not a model of scalars. This is a model of fermions. And we have 2 fermions of charge 1. And we can also add a mass. This is the model. It's a U1 gauge field and psi 1 and psi 2 have charge 1. So this is the closest you can get as an analog to QED. In 3 dimensions, you need 2 fermions rather than 1 because of some global anomaly. So you need to have two charge fermions, not just 1, if you want a nice analog of QED. So this model has received a lot of attention, and there are some outstanding conjectures about it that would be really nice to check by the Bootstrap. So I'll now quickly tell you what are the conjectures and what is believed to be true. So the microscopic symmetry. So this is the symmetry that's visible in the ultraviolet. Is SU2 that rotates the 2 fermions times U1. The SU2 is, remember that we're now in 2 + 1 dimensions, so the SU2 is clear, but the U1 is less clear. The U1 is the topological U1 symmetry that measures monopole numbers. So the charge is an integral over a space-like slice of the A. So this is like the theta angle in 2 dimensions, but in 2 + 1 dimensions, it's considered, it's like a conserved charge that measures monopoles, monopole quantum numbers. So this is the symmetry, and if you're pedantic about it, it actually combines to U2, because there is some Z2 that sits here. So there is a microscopic U2 symmetry that is visible in the Lagrangian. But then there is a conjecture. Well, there is an anomaly. There is an anomaly of the sort that we've discussed here. So there is an anomaly, and it's therefore easy to prove that this model has in fact has to be gapless. Or it may also break some symmetry spontaneously, but in this model it's unlikely. There is no good candidate. So one can almost prove that there is an anomaly, and it probably implies that the model is gapless. It's just that if you study the phase diagrams of these models and various perturbations, the scenario that it breaks some symmetry spontaneously seems rather awkward. So most people believe that it's actually gapless. Anomalies, no doubt. The anomaly has been computed. There is no doubt that there is a discrete anomaly in this system. It's written in papers. And most people believe that it's in fact gapless. And now the infrared conformal field theory is believed to have a larger symmetry. So it's believed that the U1 times SU2 is enhanced to SU2 times SU2. And I'm suppressing the divisions by various discrete factors. In fact, it combines to SO4. There is some Z, so this Z2 just goes through. And this is SO4. So this is what this is not just believed by some random guess. There are dualities and various anomalies that highly suggest that this should be true. This follows from dualities and anomalies. So this follows from dualities and anomalies, monopole quantum numbers, and many things. There are rather interesting checks of this theoretical consistency checks of this suggestion. There are rather non-trivial consistency checks of this. So what are the operators of this model? So we also have a pretty good idea of what are the local operators in this model. So it would be nice to find this model via the Bootstrap. So what are the local operators? So there is something really amusing about this model, which is that even though it has fermions, you cannot construct fermionic local operators. So it's a bosonic theory in some sense. So the Bootstrap here, you don't even need to do fermionic Bootstrap. So all the local operators are bosons. Okay, so all the monopole operators, all the gauge invariant local operators made out of the fermions, everything is bosonic. It's just impossible to write a gauge invariant fermionic operator. So it's almost a bosonic model. So there are three operators that are most certainly relevant. For two of them, I'm sure, but one I'm not entirely sure. So one operator is the singlet of SO4, and that's just psi dagger psi. That's the mass. Oh, here I added a mass, but I said that it's gapless. Of course, I meant at m equals 0. M equals 0 is a preferred point, which has time reversal symmetry, because the mass in 2 + 1 dimensions breaks time reversal. So m equals 0 is a preferred point, and this point is believed to be gapless. So one relevant perturbation is the mass. And this is extremely likely to be indeed the relevant perturbation. If you add it to the Lagrangian, you can integrate out the fermions, and it seems that the model flows to some TQFT. So it's very unlikely that this is not relevant. So this is a singlet. Then there is something very amusing. You can try to consider psi dagger psi ij. And now you can subtract the singlet. So in what representation of SU2 times U1 would that be? So the psi is an SU2 doublet. So when we multiply two SU2 doublets, what do we get? Now we have to multiply them subtracting the identity. So we get the three-dimensional representation of SU2. So 3 of SU2, and it's a singlet of U1. Okay, so these are the microscopic quantum numbers of the fermion bilinear. It's a triplet of SU2 and a singlet of U1 topological. Is it clear? However, I told you that the symmetry is supposed to be enhanced to SO4, and this is not a good representation of SO4. So this is the main, in my opinion, piece of evidence for the symmetry enhancement. So there are also monopoles in this theory. So there are monopoles, which 2 units of monopoles. So if you construct operators that have 2 units of monopole charge, and you dress them up with some fermions, you find exactly 6 additional operators that transform in the right representations of SU2 and U1, such that the whole thing fills out the 3,3 representation of SU2 times SU2. So this is a 9-dimensional representation of SU2 times SU2. So that is the traceless symmetric tensor of SO4. Right? Yes. So this is traceless symmetric of SO4. Traceless symmetric of SO4. So this is really magical. That the monopole operators that you can just quantize the monopole operators semi-classically, and they have the exact right quantum numbers to fill out the traceless symmetric of SO4, which is fantastic.
In your notation, M2 is the bare monopole?
Yes, M2 is the bare monopole. And then you dress it up with some fermions, and then the monopole picks up funny quantum numbers, and the quantum numbers exactly work out like that. So we have a singlet of SO4, we have a traceless symmetric of SO4, and there is also a vector of SO4 that comes from the bare unique monopole operator dressed with 1 psi. So, and it's complex conjugate. This plus the complex conjugate. And also here, I should have added a complex conjugate. To get these 6 necessary operators, you need to add also the complex conjugate. So these guys also magically combine to an SO4 representation, which is, in terms of SU2 times SU2, the 2-dimensional representation times the 2-dimensional representation, which is a vector of SO4. So it's absolutely clear that this is relevant. That this is a relevant operator, and it's also absolutely clear that this is a relevant operator. The traceless symmetric of SO4 should be a relevant operator because it's in the same multiplet as some bilinear in the fermions, and this seems to drive the system to some other phase. If you just add it to the Lagrangian, it flows to some compact scalar. So it's extremely hard to believe that this is not relevant. And if so, this also has to be relevant, because this is just one monopole dressed with a fermion. If the 2 monopole dressed by 2 fermions is relevant, then this should also be relevant, because this guy is in the OP of this guy with itself. So it would be inconceivable that this is not relevant. So in summary, this model is believed to have SO4 symmetry, and it's strongly believed that it has a singlet, symmetric traceless tensor, and vector of SO4 as relevant operators. in these representations. And this is supported by many consistency checks from anomalies, from RG flows, dualities, and this kind of computations of monopole quantization. This is one key example, one interesting example to concentrate on if you want to verify interesting recent conjectures in condensed matter physics and high energy physics.
Are the t-squared keys you get from different signs of the mass deformation different?
Very good question. I'm happy to see that there are sophisticated people in the audience. In this particular case, no. It's not, well, you're asking if this is surprising?
That there's a gapless point between two same phases.
Okay, since you asked, can I take a minute to answer, or preferably after the lecture?
1 minute, sure.
Okay. So in the axis of the M's, there is one mass, which is the singlet mass perturbation. So there is this operator. If we add this operator, then the phase diagram looks a little silly. Like there is this point, which is a CFT with enhanced SO4 symmetry. But if you deform by this mass, you get the Chern-Simons theory, which is called U1 level 1, and here you get U1 level minus 1. But these are trivial theories. These are trivial Chern-Simons theories. So in fact, there is no phase transition as a function of this variable. It's just like a funny CFT that appears without it, because this is a time reversal invariant point. But you get a nicer picture if you, well, you could also try to deform by the other mass, which is a triplet of SU2, or in the language of the CFT, a traceless symmetric representation. So this is a mass that would preserve, out of SO4, it would preserve SU2 times U1. So this is another deformation. In this deformation, so there we have again a CFT at the origin, but here we have a here we have a superfluid, meaning a compact scalar, and there is a superfluid here. So again, there is no phase transition, which is weird. You could have been, but you see that these two pictures cannot go. I mean, if this was a trivial theory, this would have been quite bad. So just from these two pictures, you must conclude that it cannot be that there is no transition, because here there is a superfluid at finite mass. So this mass is the one that preserves SU2 times U1 inside SO4. So in terms of the Bootstrap quantum numbers of these local operators, and this is the mass that preserves SO4. So from this diagram, you could have concluded that maybe there is nothing here, but then you would run into a contradiction. So in fact, you should plot a bigger phase diagram, like maybe 2-dimensional or even 3-dimensional phase diagram, because there is also a mass perturbation that preserves U1 times U1, and also a mass perturbation that preserves the diagonal SU2 in SO4. So you should plot like a higher dimensional phase diagram and see what are the phases. In fact, nobody did that. But it's clear that it cannot be just empty. Okay.
Are you aware of someone?
Well, Luca is the world expert on this.
No, but there are some unpublished results by David, which are reviewed in our numerical bootstrap.
Luca is the world expert on that. I would
Luca is a part of that. But,
I would hesitate to make a comment.
but there are some bounds which contradict this picture.
No, this is for the LVBS transition. This is something else.
No, there are bounds also for this one.
For QED?
Yeah.
Well, I've never seen such bounds. And in fact, there is a Lattice study by Narayanan and Kartik from just a few months ago. The one thing that I didn't tell you is that there is another discrete symmetry which exchanges these two SU2s. So there is a discrete symmetry that exchanges these two SU2s. So in fact, it's not SO4, it's O4. I didn't tell you this fact because it's not very important. But you could have seen it from the quantum numbers here. All the representations have the same number on the left and the right. So there is such a symmetry. So a prediction is that the monopole conductivity, like the 2-point function of the current for the U1 monopole, should be the same as the 2-point function for this U1 that is embedded in the fermions. And these Lattice people have simulated this model, and they found that this is true to a few digits. So this is already a sign that there is some enhanced symmetry in the infrared.
No, but the problem is not with enhanced symmetry. In fact, the Bootstrap bounds that
Uh-huh.
a very good job describing that. It's precisely the same situation as in LVBS. So under the assumption of enhanced symmetry, you show that some results that people measure with many digits are inconsistent with Bootstrap bounds and assumption of having a unitary CFT. So it might be again a weakly first order phase transition.
No, but the Lattice people here found a gapless. The Lattice people.
First order phase transitions sometimes have a huge correlation length.
Yes, it could be that the correlation length is like 2000. We were misled. Yes.
But you should be prepared to contemplate.
Yes. I think that's where the Bootstrap can contribute. That's why.
We already contributed.
Yeah.
Not simply paying attention.
Well, but this is not conclusive yet. There are non-conclusive Bootstrap results, non-conclusive Lattice results.
No, the results, Bootstrap results are conclusive. The Lattice results may not be conclusive.
Well, the Lattice results are, I think, very clear. The Lattice results are very clear in my view. So, okay.
Results have error bars. Bootstrap results have no error bars.
We'll see.